I'm sorry, I forgot to record this again. I don't know. Did you look at the last recording at all?
I went back and went through some of it when I was doing some of the other homework problems for that chapter one.
I'll have to make more of a point of turning it on. I don't know why. I think both times I've forgotten to turn it on for the first 30 minutes of our session. But I've turned it on now, so I apologize. Okay, a ladder. The ladder wall problem. Here's the wall. And we have a ladder leaning up against it. The ladder is 25 feet long. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. What does that mean? If I set this up on an XY axis, what does it mean? The base of the ladder is pulling away from the wall at a rate of 2 feet per second.
That's negative 2x.
But what is that equal to?
Dx dt.
Exactly. In other words, it's a rate. When you see the word rate and per second, we know we're talking about dx dt. So that's negative 2. And that's correct because it's moving in this direction. If it was moving to the right, it would be positive 2. If it was moving up, dy dt would be positive, and if dy dt is moving down, it's negative by convention. So what do they want here? They want how fast is the top moving down the wall when the base of the ladder is 7 feet and 15 feet. Okay, so if this is 7 and this is 15, I don't think this is going to matter which one is which. When the base of the ladder is 7 feet and 15 feet. Okay, I'll interpret it like this and see if it matters, whether the 15 goes here and the 7 goes there. But give me a master equation that we're going to be able to implicitly differentiate to come up with our differential expressions.
Basic ladder.
So right triangle.
Yeah.
With
So
a wall.
On the ground is all. I don't know. Would we just be doing? I want to say the area of a right triangle, but that wouldn't be right.
How about the Pythagorean theorem?
So
X squared plus y squared equals 25 squared. In other words, the hypotenuse squared is equal to the sum of the sides squared.
Side squared.
Well, that's our master equation relating x and y. And all of their questions are asking or giving information about dx dt, and what they want is dy dt. So we want to look for a master equation that relates x and y. And this is it. So let's implicitly differentiate this with respect to dt.
So we get 2x dx dt plus 2y dy dt equals 0.
Okay. Trying to solve for that. And we have 3 unknowns, x, y, and dx dt. Well, they gave us dx dt, and they're giving us the x and y. Now, is it going to matter which we use, 7 and 15? Looks to me like it might matter. I don't know. Let's solve it. Let's assume that I've labeled it properly here. They're not real specific in their telling us what the base and the distance is here as to which is x and which is y. So 2x is going to be 30. dx dt is 2 plus 2y is 14. And we're trying to figure out dy dt. Now, let's see. I said 2, but I really meant minus 2. So I've got 14 dy dt equals 60. Right?
Yeah.
So dy dt is 60 divided by 14. Which begs the question is, why are we getting a positive sign here? We know it's slipping. So there's no question that dy dt is moving in this direction at a certain rate.
Yeah.
So we know what to answer. What sign is attached to it perhaps is irrelevant, especially when they ask about speed, not velocity. They merely want to know how fast the top is moving down, so the sign really doesn't matter. The difference between speed and velocity is speed doesn't have a sign attached, velocity does. So they've spared us that question. So the answer is 30 over 7 feet per second down the wall. So that means that it's sliding faster down the wall than it is along the base. Because the base it was only going 2. This is closer to 4.5. Guess that makes sense. Alright, let's see. Consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. Which leads me to believe that I put these dimensions on here incorrectly. Notice that with everything they've given us, the base of the ladder is never 7 feet from the wall. So I must have put them on there backwards. This must be 7, this must be 15. And the question is, does that change our answer? No, it doesn't. We still end up with 60 divided by 14. Okay, so for this question, they want to know the rate of change of the area. So what do they want to know? What differential do they want to know?
They want to know the ADT.
Uh-huh. Which means we need the formula for area.
1/2 base times height, so 1/2 x1.
So let's implicitly differentiate this with respect to t.
So the ADT equals
Now, this is a little tricky because you need to bring in the product rule.
1/2 and then parentheses x dx dt plus y dx dt.
The first one was 1/2 x dy dt plus
Y dx.
plus y times 1/2 dx dt, right?
Yes.
In other words, I'm going to take the derivative of that. No, I'm going to take that times the derivative of that, which is that. And I'm going to add to it the derivative of this times the I'm sorry, this times the derivative of that, which is 1/2 dx dt. So yeah, this looks right. Okay. And what do we know? We know dy dt, we know dx dt, and we know x and y. So solving for dA dt is a question of plugging in. Now the only reason we know dy dt is because we solved it, or I'm sorry, dx dt is we solved it in the first question. So what do we have? We have 1/2, and we decided x was 7, and dy dt was 60 or 30/7 from part A, plus y, 1/2 y, 15 times dx dt, which is 2. So your answer should be 15 plus 15, 30. The area is changing at 30, has to be square feet per second.
Yeah. Yeah.
Now, the question is it increasing or decreasing? Let me draw this more accurately. I drew it as an isosceles triangle. Let me draw it like it really is. Okay, so this is our model. The ladder is right here. It's slipping down. Is that area increasing as it slips or decreasing?
Wouldn't it start out increasing?
Yes. Now, the only reason I know that is I know that maximum area comes from as close to a sphere as you can get. In other words, either as close to an isosceles triangle or an equilateral triangle, or if you're talking rectangles, a square gives you the most efficient area per perimeter. So I know that this area is increasing until y is equal to x. Yeah. Once y is equal to x, it's going to start decreasing again. So by looking at the model, I know that we have an increasing area, which is what we got, but I didn't pay a whole lot of attention to the signs on dx dt or dy dt. But I guess one thing we could say for sure is they're both the same. In other words, if we look at that ladder falling, and you don't have to say going to the left is negative. You can choose to call it positive. But we know that as the ladder slips, x increases and y decreases. But x increases to the left. So actually x is negative and y is negative. And area, or you could say x increases is positive, y is positive, so their area is going to be positive. That doesn't make any sense. Well, for the moment, let's just stick with the fact that we know it's increasing until x and y are. So regardless of what sign we came up with, we know what sign to put on the final answer. Plus. Find the rate at which the angle between the ladder and the wall of the house is changing when the base of the ladder is 7 feet from the wall. Okay, now we're getting a little bit harder because we're dealing with angles. So again, This is 7, this is 15, that's 25. And this angle is the one they're requesting. I believe the angle between the ladder and the wall. No, they're talking about this angle there.
Yeah.
So they want to know d theta dt. So what equation can I use to relate theta with x and y?
The tangent of theta is x1.
Right. So it's equal to x over y. But they want d theta dt. So I have to solve this master equation for theta before I do anything. So theta is equal to inverse tangent of x over y.
Now we would implicitly.
Now I can differentiate this and come up with a d theta dt. In other words, we weren't looking for d tangent theta dt. We were looking for d theta dt. So we have to first solve for theta by taking the inverse tangent of both sides, essentially. Now we have theta. And what do we know about inverse tangent? You remember what the derivative of inverse tangent is? It's equal to 1 over 1 plus x squared. Oddly enough, when you take the derivative of the inverse trig functions, you get polynomials. You don't get trig functions. If you take the derivative of trig functions, you get other trig functions. But when you take the derivative of inverse trig functions, you get polynomials. So we want to take the derivative, only we're taking the derivative of x over y. So we're going to have to use the chain rule by taking the derivative of this and then multiplying it by the derivative of the inside, which is x over y. Okay? So, let's begin, because this gets a little hairy. So the first thing we're going to do is say 1 over 1 plus x over y squared. In other words, for the moment, the inside is x. So that x is x over y squared. And then we have to multiply this by the derivative of the inside. So we need to know what is the derivative of x over y d theta. Hold on a second. Is it d theta? Yeah. No, dt. Excuse me. We're trying to find d, everything with respect to t. So let's we have to multiply this by the derivative of this. You remember your quotient rule? Chase? Chase, did we lose audio? You can hear me, I can't hear you. Did perhaps you accidentally turn your microphone off?
Can you hear me now?
Yes. Yes, whatever you just did worked.
I bumped the mute button on my mic.
Okay, I've done that many times, so that's the first thing I thought of. Was I frequently hit the power switch or the mute button on my mic. Okay, so here's the derivative of the outside. And we have to apply the chain rule by figuring out the derivative of the inside, and to do that we need to apply the quotient rule. Do you remember the quotient rule?
Was that the, you take the bottom derivative, you take the bottom times the derivative of the top minus the top derivative of the bottom all over the bottom squared?
Exactly. So let's do that. It's the bottom times the derivative of the top, which is 1, but since it's x and not t, we have to follow it with that, minus the top times the derivative of the bottom, which is dy dt, all over the bottom squared. So there's our formula for d theta dt. Now, what do we know that we can plug in? We know that x is 7 and y is 15. And we know that dx dt is 2 and dy dt was 30 over 7. That's all the variables. So the rest just becomes algebra, which we would probably be better off not spending our time doing the algebra.
Yeah, algebra, I understand.
Once we get it set up, getting it set up is always the difficult part here on these related rate problems. Although the algebra can sometimes be a little tricky. All right, let's go look at the last one here. Okay. You can imagine that the formula we're going to be using here has to do with the volume of a cone or the surface area of a cone, right?
Yeah.
Since we're looking at a cone. I haven't yet read the problem to find out what they're asking, but it's leaking water at a rate of 2 cubic feet per hour. What information did they just give us?
dv dt.
And in this case, I'm definitely going to put a negative sign with it. The base of the tank radius is 5 feet and the height of the tank is 14 feet. Okay, in other words, the tank is this outside triangle here. And at what rate is the depth of the tank and the tank changing when the depth of the water is 6 feet? Okay. So what is our formula for volume of a cone?
1/3 pi r squared h.
Okay. Since they give us dv dt, we know we need to implicitly differentiate this. Help me out here.
Is 1 times.
So you can treat that as one variable, and that is your second variable, and apply the product rule.
So we would get give me a second.
Your audio might be getting a little choppy. I didn't hear what you said.
Oh. Maybe I bumped my mic again, sorry. So we would go H,
Okay.
right? The particle, H, and then the derivative.
The derivative of this, which is 2/3 pi r
Yeah.
dr dt.
T.
Okay, so
Then
that's
we
the
have
first part of the product rule.
Plus, we just the 1/3 pi r squared, and then the derivative
dh dt.
T. Yeah.
Okay, so there's our dv dt. And let's see, what are the unknowns? They've given us this, so we can plug in -2 for that. They have, all right, we need to relate, hold on a moment. At what rate is the depth of the water in the tank changing? So they're looking for dh dt.
And we know.
We don't know dr dt. Let's see, we're trying to find dh dt. So if we were to define r as a function of h, we would be in like Flint. Can we define r as a function of h? Yes, r is equal to 5, r over h equals 5 over 14. By similar triangles. In other words, we're looking at this triangle here, which is r over h, and this big triangle is 5 over 14. They're similar triangles, so this has to be true. So we can actually define r as a function of h from the get-go. And then we'll be differentiating with one variable only. We won't come up with a dr dt. We will come up with strictly dh dt's, and we'll need an r and an h, but they give us that in A. When the depth of the water is 6 feet, we can also figure out what the radius is, so we can fill in r and h. I don't want to leave you with that. We got a few minutes here. Let's just go through what I was talking about there. I went through it kind of quick. So let's go back to here. We could actually figure out dh dt also from this, but I think it makes more sense if we do it like this. We are going to substitute for r. Well, r is that. So now v is 1/3 pi times 5h over 14 quantity squared times h. Now dv dt is, this becomes what? H cubed. Now we don't even have to apply the product rule. We end up with 5, let's see, 3 times 3, so we end up with 5 pi over 14 h squared dh dt. They gave us dv dt. what was dV dt? That was 2 feet per hour negative. So this is minus 2 over here. 5 pi over 14. They said when the height was 6 feet. So 6 squared. dH dt. Notice that dH dt will be negative also when we solve this.
Yes.
That exactly makes sense. The height is going down.
Mm-hmm. Well, losing water.
Yes. In other words, the radius, while it's losing water, the radius is decreasing and the height is decreasing. The important thing is all of our signs are consistent with one another. They're all negative in this case. I suppose we could have left them all positive to begin with, and we could say that it's decreasing at a positive rate of this. But at some point, you do have to incorporate the direction in these problems. Otherwise, because sometimes you'll have ones decreasing and the other is increasing. And the signs won't all be the same. So, notice the second part of this question asks you at what rate the radius is changing when the depth is certain. Okay, so we would have to do it a little different. In other words, to solve that, we don't want to turn this volume into a function of h. We want to turn it into a function of r. So I would solve for h. H is equal to 14r divided by 5. Substitute that in for h, ending up with a function that's completely a function of r. You with me?
Yes, I am.
Implicitly differentiate it. You'll have a dV dt. You'll have a dr dt. You're given the dV dt. You can solve for the dr dt, and that's what they're asking for, is what is the rate the radius is changing. All right, why don't we end it there? All of these are pretty much the same. If they're geometric figures, then you know that you're going to have to relate r to h, like we did in this problem here. All right, Chase. I hope that's been helpful. That's a difficult topic to try to master in 1 hour. But let me know if you feel like you need additional help on it. You can schedule another session if you want.
Okay.
Okay?
Okay.
I will talk to you next week unless I hear from you.
Okay.
All right.
And then Mom had a question. She didn't get the invoice from last week.
Okay. $32 a session. I can send. I sent it to you? Is that what?
I didn't get it either.
You didn't get it? Give me an email. Oh, I sent it to LA Dragon.
She said she didn't get it at that email.
Okay, I'll send it again. At this point, we've only had 2 sessions, so it's 64 bucks.
Okay.
Okay, and she can just, if she's going to use PayPal, she just sends a PayPal payment to my email address. Is all she does.
And that's what she was planning on doing.
Yeah, then it's real easy. Just have her log into the PayPal account, send money when they ask to what? DavidCowan1949@gmail.com. And I will resend that invoice, but I'm pretty sure I sent it once. But maybe I forgot to. I don't know. I'll resend it.
Okay.
All right? Okay, Chase. Talk to you later.
We'll talk to you next week.
Bye-bye.